A major activity in statistics is the building of statistical models that hopefully reflect the relationship between variables of interest with a certain degree of realism. The aim of regression models is to construct mathematical representations which describe, explain, or predict one variable using a set of other factors. Dependent variable is also known as the response or the outcome variable. Independent variables are also known as predictors, regressors, explanatory variables, covariates, or input variables. Variables are measured. Parameters that appear in a regression are unknown but can be estimated from the data. The error term, the epsilon that appears in the regression equation that you have in front of you, is unobserved and considered to be the cumulative effect of all the variables that affect the dependent variable and yet are not included in the regression model. For example, it may be the cumulative effect of factors such as the examiner experience, inventor experience, the budget of the patenting office, and other factors that we do not currently have in the model, but which may affect the examination times. In regression models, often extra care should be taken to ensure that the independent variables entering the model are not strongly correlated among themselves. If such a correlation exists, it results in unstable parameter estimates and can complicate the interpretation of the estimates. That is called multicollinearity, and effective approaches exist to account for multicollinearity. The model that you have in the slide is called the multiple linear regression model. Multiple since there is more than one independent variable on the right-hand side of the equation, and linear since the right-hand side of the equation is a linear function of parameters. There are a host of nonlinear models, some of which are pretty popular and include Poisson regression and logistic regression, which are special forms of regression that work for modeling discrete and categorical outcomes, respectively. In case there is only one independent variable on the right-hand side of the equation, the model is called a simple linear regression. It's important to remember that certain assumptions are stipulated on the error term. Errors are assumed to be identically distributed with mean zero and constant variance. Errors are assumed to be independent. And in addition to these assumptions on the error term, it's also assumed that the postulated relationship is correct. In a nutshell, what the regression assumptions mean is that when describing the variation in examination times, accounting for only the factors that appear on the right-hand side of the regression equation, the remaining or unexplained variation in examination times does not have a predictable or systematic information, such as patterns that we in fact could explain had we more effectively carried out our modeling. In addition to these assumptions, usually the normality of the error term is assumed, and that comes handy when carrying out inference for the regression parameters and predictions for relatively small samples. One thing to keep in mind when it comes to regression assumptions is that these assumptions should not be taken as granted and should be checked. The framework and methodology for checking regression assumptions is often carried out using so-called residual diagnostic analysis. We will briefly discuss residual diagnostics in the next video. Here is something you should remember though, that what we are modeling is the expected value of the exam time, not the time itself. In other words, what we are trying to model for regression is the average examination time for a patent document with a given number of prior efforts, a given number of inventors responsible for it, and a certain claim volume. In the formula that you have at the bottom of the slide, EV is an abbreviation of an expected value of the examination time of a patent application with characteristics that appear on the right-hand side of the regression equation. How do we build a regression model when the ultimate objective is predictive modeling? First, we have to remember that we need to estimate the values of the unknown parameters. These betas that appear in the formula are unknown, remember. And a number of software have capabilities to do so. and ordinary least squares method is the standard method used to estimate the values of the parameters from the data as well as the variance of the error term. One thing to remember, however, is that in predictive modeling, the parameters are not estimated based on the entire observed data. Instead, parameters are estimated using a random subset of the data. In particular, we split the data into two pieces, the training and the validation sets. Then we estimate the parameters, in other words, build the model using the training set, and then evaluate the accuracy of the model using the validation set. This method, which is called the holdout method due to holding out part of the data for validation purposes, can be and is often further complicated by iteratively repeating the sampling process to ensure that the results we get are not biased due to random selection of just one data set. This approach is often referred to as the k-fold cross-validation, and we won't discuss it here. Now, we will apply the described holdout method for the pattern data. We will randomly split the data provisionally into 45 observations to be used as the training set, and the remaining 5 for the validation set. The 5 elements that make it to the validation set due to the random selection are given on the slide. Notice the hat on top of the EV on the left-hand side of the regression equation. That simply denotes that what the given equation represents is the estimate of the mean examination time.